Lesson 84, multiplication of radicals. So let's go back in our memory and think about radicals. Radicals are these little square root symbols, and they have numbers under them. And we're trying to find perfect square factors out of this number. And we know we can rewrite this as 5 times, or the square root of 5 times the square root of 5 times the square root of 2, because the square root of 5 times 5 is 25 times 2 is 50. And because we got two matching factors, radicals, we can pull those out and put them on the outside, and then we end up with 5 times the square root of 2 is the simplified form of the square root of 50. Okay, so we know that's called the product of square roots rule, and it just says if m and n are non-negative real numbers, then we can pull those factors out and write them like this. That's all it is. So let's look at 83.1. Let me clear this page. We're going to use or 84.1. We're going to use a little bit more complicated radical problem, and we're going to use that rule to solve the problem. So we're told to simplify 4 times the square root of 3 times 3 times the square root of 2. Now we can do this easily. We treat the whole numbers just like whole numbers. We say 4 times 3, that's 12. And we treat our radicals just like numbers as well, like factors. And what they look like is square root of 3 times the square root of 2. That ends up the square root of 6. We just multiply the 3 and the 2, and we keep the radical or the square root symbol over the top. And then that's as simplified as we can get this problem. So now let's move on to 84.2. And we are asked to simplify 4 times the square root of 3 times 6 times the square root of 6. Okay, we can treat our whole numbers the same. 4 times 3 is 24, but we have the square root of 3 times the square root of 6. Well, the square root of 3 times the square root of 6, square root of 6 can be broken down into the square root of 3 times the square root of 2. And because we have two matching radicals, we can pull that 3 out as a factor, and then we have the remainder of the square root of 2. So this becomes 72 times the square root of 2. So just because you can multiply, this is 3 times 6 gives you 18, don't leave it there. You can simplify it even more by factoring out your radical. So that's the next step to do. All right, 84.3, I think we can do it here. We are asked to simplify 4 times the square root of 3, and it's a distribution problem of 5 times the square root of 2 plus 6 times the square root of 3. Okay, so we distribute. We use our whole numbers first. 4 times 5 is 20. So 20, and then we have square root of 3 times the square root of 2. It's going to be the square root of 6 plus. We have 4 times the square root of 3, or I'm sorry, 4 times 6 is 24. And then we have square root of 3 times the square root of 3. Well, those two radicals match up. We can pull them out as factors, and we can multiply. So we are left with, we simplified to 20 times the square root of 6 plus 72. Okay, that would be your final answer here. 84.4 is our last one. And we are asked to simplify 4 times the square root of 2. And we distribute again 3 times the square root of 2 plus 5. So 4 times 3 is 12. And the square root of 2 times the square root of 2, well, those two match up and become a factor. So now we have times 2. 4 times a positive 5 is going to give us a positive 20. And we have square root of 2 times, really, no variable. So we just bring this square root of 2, this radical sign just comes down here to the bottom, and we add it to this term. So now we multiply these. 24 plus 20 times the square root of 2 is our final answer. And you can see how simple that is. You just take your whole numbers to your whole numbers and your radicals to your radicals. And if there's not a radical, you just drop it down. And that's all there is to that. All right, that's all we had on radicals. Now let's talk about functions for just a moment. That's the second part of lesson 84. We are going to talk about what's called a function machine. So we have this thing, this little box right here in the middle. Okay, close enough. And this is going to be our function machine. You do not have to draw this on your paper. This is just an illustration to help you kind of understand where we're going. But if anybody ever asks you, hey, do you know what a function machine is? Now you know. It's just a box. It's just a box. Now, we know that our x values are the domain, and we know that our y values are called the range. Okay? So our domain in this function machine, we are given 2, 4, and 7, and our function is x squared plus 5. Now we're going to plug these x values into our function machine, and we're going to get a result, which in this case with a function machine, your y value, your resulting y value is called the image of the x value. So in that case, the image of 2 squared is 4 plus 5. The image of 2 is going to be 9. The image of 4 is going to be 21. And the image of 7 is going to be 54. And if you want to check that, 4 times 4 is 16 plus 5 is 21, and 7 times 7 plus 5 is 54. So this is just a picture of how we get to our domain and range illustrations that we're going to be showing you next. Basically what it does is it skips this little box here in the middle. It doesn't matter. It doesn't care what the function itself is. All these illustrations care about are the x values and the y values, the domain and the range. So let's move on to that. It's just trying to get you to understand how that got there. So we have a couple of illustrations of a function mapping, or they also call it a correspondence. So this is a function, it's supposed to be C, function mapping or correspondence. And the reason they call it a correspondence is that an E or an A? It's an E. Is because the x values correspond to a y value. So we see in this one, the first one, our domain and our range are illustrated for us here. We are given that we have a domain of 4 and 2 and a range of 3, and both of these have the same y value. So the x values are 4 and 2 and the y value is 3. This might illustrate a function something like maybe y equals 3, so that every value of x is going to equal 3. We have those sometimes. That's possibly the case, but with this illustration, we don't care how it got there. We just care about the answers that we have. We are just analyzing the ordered pairs that we have received. That's all we're doing. So in this case, the definition of a function, it's going to require that, let me write it out for you. A function must have one y value for every x. Okay, so one y value for every x. In this case, 4 has 3 and 2 has 3. So every x value has a y value. So this is a function. Okay, here's another one that we're given. And you can tell me if this is a function or not. Here's our domain, and I'm just going to write a D and an R just for quickness purposes. We have 4, 2, and 1 are x values, and 3, 5, and 6. And 4 maps to 3, 2 maps to 5, 1 maps to 6. Okay, does every x value have a y value? Is there one y value for every x value? Yes, every x has a y. So this is a function. Both of these are functions. All right. Now, a function, if it's a function, that is the definition. But a set of ordered pairs can be something other than a function. They can be a relation and not a function. And go ahead and put this in your notes. Function must have one y value for every x value. A relation, I'm going to put this over here. A relation, on the other hand, just says that every x value must have a y value. Let me reword this. The function must have one y value for every x value. X cannot have two, or let me rephrase it, more than one, cannot have greater than one y. Okay, so x must only have one y value in a function. In relation, every x value must have, let me rephrase this, at least one y value. Okay, a function must have one y value for every x value, and an x cannot have more than one y value. You know, it can't have 2, can't have 3, it can only have 1 for each value of x. A relation, on the other hand, x can have more than one y value. So x could have 3 y values as long as each x has a y value. That's all that a relation cares about. So those are your two different definitions, function or a relation. All right, so let's look at some exercises and let's see the difference. Rewind and make sure you get this in your notes because that's going to be an important definition, an important distinction. Let me give you a couple of pictures of some relations, or this is a picture of a relation right here. Here's your domain. Here's your range. All right, we have 4 and we have 2. We have 3. We have 5 and we have 6. All right, 4 maps to 3, 4 maps to 5, 2 maps to 6. This is not a function because 4 has 2 y values. But it is a relation because each of your x values does have at least one y value. So that's the difference. This is the picture. This is not a function, but it is a relation. Now, a relation can also be a function. A function is also a relation. So you can have a relation and it not be a function, but if it's a function, it is also a relation by default. Okay. Now here is a picture of a set of ordered pairs. Here's the domain, here's the range. And we have a 4, we have a 2, and we have a 1. Well, 4 maps to 3, 2 maps to 5, 1 doesn't have a y value. So if this one doesn't have a y value, this is not a relation either. It's not a function or a relation, because this last little fella down here doesn't have anybody. He's all alone. So if you have an x value that's all alone, then it's not a function and it's not a relation. Okay? Something like what we had on the other page, where we have a domain and a range. We have a 2 and a 1, and we have a 1 and a 2. And each one, this is both a function and a relation. Absolutely, because it's a function because each x value has only one y value. And it's a relation because the x value has at least one y value. So it's true for both of them. So I hope you can see the difference. This is a relation but not a function. This is not a relation or a function. And this is a function and a relation. And typically, if it's a function, it is a relation. Okay, by definition. All right, let's do some example problems with this. All right, let's do 84.5. So here is our domain, and here is our range. And we have x values of 4, 5, and 6, and 4 maps to 7, the 5 maps to 2, and the 6 maps to 14. Is this a function? If you said yes, you are correct, because every x value has its own y value. Okay? No x value has more than one y value. And they all have one. So yes. All right, 84.6. What about this set? We have, here's our domain and our range, and we have the letter y, a, and m. So it doesn't matter. It doesn't have to be actual numbers. It just has to be something that is a picture of a value. And then we have the number 5 here. So in this case, y maps to p, a maps to x, m maps to x, but m also maps to 5. Is this a function? No, not a function. Is it a relation? It is a relation. And it is a relation because every x value has at least one y value. Everybody's paired up with somebody, and it's okay if they get paired up more than once. They're having relations. All right. Or relationships. So 84.7 is DNR. The domain in this problem, we are told lowercase a, 4, and 7. And a maps to 5. 4 maps to 5, 7 maps to 11. Is this a function? Yes. If you said yes, you're correct, because a only has one value, 5, 4 only has one value, 5, and 7 only has one value, 11. It doesn't matter that a and 4 have the same value. It doesn't matter that the y is the same for both of those. What matters is that x only has one pair. All right. Is this also a relation? Yes. And it is also a relation because a, 4, and 7 all have a y. They have at least one y, so they're good. All right. In 84.8, we don't really have any limitations on our domain. We are told that the realm or the domain is all the real numbers. It's a set of all real numbers. And our range can then be specified with this formula, that y equals x plus 2. So we can plug in any real number in the domain, and we can get a value, a y value in x using this function right here. So is this a function? Yes, because we can plug in any number and get a response for y. So this is a function. It's also a relation because whatever x value is, you can get a y value for it. So it's both. Okay? Let's move on to 84.9. And let's look at this a little bit differently. In this, we are given some sets. We're given A, and we're given a set of ordered pairs. And our sets are as follows: 4 and 6, 7 and 2, and 4 and 5. And that's in A. And then in B, we are given this set. And we have 4 and 8, and 15 and 6, and 11 and 7. All right, is this a function? Let's see. We can draw our little sketch here if we want to. You don't have to, but it sure helps to solve the problem. We have a 4, we have a 7, oh, and we have 4 again. Well, we have 4 maps to 6, 7 maps to 2, and then 4 maps to 5 again. That is not a function because 4 has 2 possible y answers. So this is not a function. It is a relation, but it is not a function. All right, for B, what do we have? In our domain, we have a 4, we have a 15, and we have an 11. And in our range, we have 4 maps to 8, 15 maps to 6, and 11 maps to 7. Is this a function? Yes. It is a function because each x has only one y. Okay? Let's move on. Let's do 84.10. And we have 4 sets of ordered pairs here, and I'm just going to write them out. So A is 1 and 2. You can copy with me as we go. So maybe this won't take so long and be so boring, me just sitting here talking about the x and y values in this set. All right, so let's look at these. Let's do A first. All right, so we have 1, 2, 3, and 4 in our domain. Okay, in our range, 1 pairs up with 2, 2 pairs up with 3, 3 pairs up with 4, and 4 pairs up with 5. Okay, that's a function, yes. Easy peasy, right? Each one of these has its own number. So we know by default that this is indeed a range. Or, I'm sorry, a function, so yes. In B, we are given this set of ordered pairs. We have 1 and 2, 2 and 3, 1 and 3, and 4 and 5. All right, so just looking at the x's here, we have 1, 2, we have 1 again, and 4. All right, so we have 1 twice, and in both instances, it's matched with a different y. So this cannot be a function because we have 1 and 2 here, but we have 1 and 3 here. So let's illustrate it and make sure we're right. We have 1, we have 2, we have 1 again, and 4. All right, and 1 goes to 2, 2 goes to 3, 1 goes to 3, and then 4 goes to 5. So no, this is not a function because 1 has more than one answer. So it's not a function. It's a relation, but it's not a function. All right, in C, let's check out and see if we think that it is a function. So we have 4 and 3. We have 2 and 2. We have 4 and 3 again. And we have 3 and 3. So just looking at it, just looking at our sets of ordered pairs, we have 4 twice, but both times it's paired with the same y. So that tells me that that's okay, because each time we come across the 4, we get the same answer as y. And that's okay. We get 3 and 3. All right, so we get 2 and 2 together, and we have 3, but it's also paired with 3. Is that okay? Well, let's take a picture of it. We have 4, we have 2, and we have 3 as our different x values. And 4 goes to 3. Okay, that's right. 2 goes to 2. 4 goes to 3 again, so just another line there. And then 3 goes to 3. Is it okay for 4 and 3 to share the same y? Yes, that is okay. So this is a function. We only have one x value, or each x value only has one y value. So the y value can have more than one x, but the x can only have one y. So this is a function. All right, let's do the last one here. D, and here's our ordered pairs to look at. We have a 1 and a negative 1. We have 4 and a negative 1. We have negative 1 and a negative 1. And we have 3 and a negative 2. So let's see, we have 1, 4, negative 1, and 3. That's in our domain. 1, 4, negative 1, and 3. That's our domain. And our range, we have 1 goes to negative 1. 4 goes to negative 1. Negative 1 goes to negative 1. And 3 goes to negative 2. Is that a function? Yes, because each x value has one y value. So that's all that's necessary. So yes, this is a function. All right, do we see how that works now? All right, so let's clear this page. We have another example, 84.11. We have 7 and 6 in our domain, and in our range, we have 11, 4, and 8. 7 maps to 11, 6 maps to 4, and 6 maps to 8. Is this a function? No. Why? Because 6 has 2 answers. The x value of 6 has 2 y's. That can't happen. So the answer is no. It's not a function. Okay? One more. Let's do 84.12, and then we'll be done. We have a domain here, and we have 6, 7, and 5 in our domain. And in our range, 6 maps to 4, and 7 maps to 11. 5 does not have a y value. Is this a function? No. Is this a relation? No. Because this x value does not have a y value. So it cannot be either a function or a relation. Okay? Is this a relation? Is 84.11 a relation? Yes. Yes, it is a relation because each x value has at least one y value. So everybody has at least one partner. So yes, it's fine. But it's not a function because in a function, we only have one x to one y. We can't double up. Right? So that's all we have for lesson 84. I will see you guys in lesson 85.